Hello everyone, I'm your host as always, Mr. Lindley. Inclines, a challenging topic for many, worthy of its own video. Let's get right into the classroom with Mr. Lindley. Thanks so much. I'm inclined to help you guys with this. You could say I'm really ramping up the review process. Let's get at it. Ramps, let's draw one. Boom, boom, boom. Got my incline. And I have some object, some mass sitting on that. Now, how would we typically start? Many ways we could do this, right? There's many things going on, so let's just think, where I would start. A lot of times with this stuff, if I don't know exactly what to do, but I'm trying to analyze a scenario, I think free body diagrams are a great spot. So let's start with an FBD for this. Now, remember, with drawing FBDs, I always put a dotted line to represent my surface. And then if I have this, let's say downward, right? Straight downward would be FG. And now for this, let's say that this is at rest currently. So we'll put that in the diagram, at rest. And let's say this is all frictiony, right? So, all right, what else would I have in my diagram? Upward, I'm going to have the normal force. And then this way, then I'm going to have the force of friction. Now remember, one of the tricks that we had done was we take our heads and we basically tilt them so that our heads are tilted like this to match the incline. Is that the right way for you? Yeah, I think so. Whatever. And what that allowed us to do was we can then not have to break Fn and Ff into components. I can actually just break Fg into components. Makes life a little bit easier. So to remind you in terms of drawing that, so I'm going to draw that off to the side. Remember, we don't draw components on FBDs. So here is theta. Now, if we draw that angle always, then that means that theta is going to exist right there. So when I draw this, when I draw my components here, I'm going to draw one of them like this. And we're going to call that FGY, and I'm going to draw another one like this, which we would call FGX, and remember that there is theta. So because that is theta, that would mean that FGY for this is going to be, if we think SOHCAHTOA, it should be adjacent, so this would be FG cosine theta, also written as MG cosine theta. And then FGX would be FG, well, it's opposite. SOHCAHTOA, SOHCAH, So it'd be FG sine theta or MG sine theta. Now, if this is at rest, we could then write our equilibrium equations for this. So our equilibrium equations for this would be up equals down, left equals right. So I would have that Fn is equal to Fgy, and I would also have that Ff is equal to Fgx. And depending on what the scenario is asking for you, is it asking for the coefficient of friction, or if it's asking for to find the normal force or whatever, we can then use this to solve. But let's say, what would happen if we have the same scenario when it's not at rest? So what if instead it's not at rest? Well, if it's not at rest, I'm still going to have Fn be equal to Fgy, because it's not going to bounce down ramps. It's a very weird question. But now I'm going to have to think about Fnet. Right? And Fnet we know always is Mom, Meatloaf! Mom! She can't hear me. I don't understand. I get she's in a different county, but ridiculous. And then if we think about the net forces here, if it's down the ramp, right, we're going to get Fgx, which always acts down the ramp, and then we'd have to subtract the force of friction. Now, where this might get a little bit complicated for us is, if I'm trying to solve for the force of friction, remember the force of friction is mu Fn. You can see that this is where it gets a little, I would have to actually solve for Fgy, because Fgy would get me Fn. Fn would get me Fn mu, which would get me Ff, which would go here. So it's like a triple jump, like a 1, a 2, a 3, a 3. So we can see all that process that's going on. It is a bit involved. Now, if we then were being asked to figure out speeds of stuff, we would then at this point not hit the help menu, because that would, I mean, on life hit the help menu sometimes, and that's what this video is, but not like the actual help menu on your screen. This is where we'd have to bring a chart in now. So we would say, V naught VA delta X delta T, making a chat. Chatty, chatty, chat. And for a lot of these problems, this does in fact start at rest. Now, how would we ever find the acceleration? The acceleration we would find from Meatloaf. We would bring that in, right? The length of the ramp, however long that is, would most likely be known, right? And if we would look, a 1, a 2, a 3, we could then, and for, for a lot of these problems, it'd be V squared, V naught squared plus 2a delta x, and we could use that to then solve for how fast it's moving at the bottom of the ramp. Now, what if we have a slightly different scenario where I have a ramp and instead there's a rope, some sort of tension that's pulling it up the ramp, and let's imagine that it is accelerating. Now, in a scenario like this, again, I'm still going to get F net here, but now tension, and then, well, if I have friction, that's going to be resistive, but FGX would also be resistive because FGX is going to act down the ramp and tension is trying to pull it up the ramp. So it is going to be different still. And I would still have the normal force be equal to FGY. So be careful with that. FGX is always down the ramp. It's not always accelerative. It's always down the ramp. Now ramps. This is where it gets kind of interesting because we don't have to do any of this if we're trying to find the speed at the bottom of the ramp. If I have my initial ramp scenario and I'm just trying to figure out how fast that thing's going at the bottom, we can use EIEIF. Nice! Because in the beginning, this should all be UG, and at the bottom, this should be kinetic. But what if this is friction, like we were talking about? Well, then it'd be kinetic and heat. Okay, we got this still. So let's try to work this out. I'm going to have UG, right? I'm going to have K plus Q. Now, UG, this is pretty straightforward for us. This is mg delta y. Kinetic energy is 1/2 mv squared plus heat. And this is where it gets a little interesting because if we think about heat, right? There's actually, in these scenarios, and this is, if you don't have friction, like, if you don't have friction, that's it. You just roll with that. But let's do the friction part just because let's make them as hard as we can. There's work being done by friction that is causing a change in heat. Now, if this is a standard scenario, which we think it is, in the beginning, there shouldn't be any heat because it's not like pre-on fire. So it means the work being done is really equal to the heat that's in the end. Now, how do we find work? Well, it's FD, right? Would be equal to my heat. So what do I need to do to find the amount of heat that's being generated? Well, it's just the force of friction times the displacement, which in this example would be the length of the ramp. All right, well, how do we find the force of friction? Well, that's mu Fn, and on ramps we said that Fn is equal to Fgy. Here's again my triple jump, a 1, a 2, a 3, a 3 to find Ff. So I'm still doing a little bit of work, but the rest of it saves me. So I still have to do the same amount of work for friction. That's not changing. But why? What's the benefit of this? Instead of doing dynamics and kinematics, right? So forces and the chats, I can just do EIEIF. Keeps everything a little compact and a little bit easier for me to do. Now, let's just, take this one step further to sort of write this out. So this would be mg delta y, right? And then this is 1/2 mv squared, and then this would be, so the force of friction would be mu Fn, and Fn is Fgy, so it's really mu, and then this would be mg cosine theta, and that would be multiplied by the displacement. And you can see this is where if I'm looking for speed, I can start to cancel things and simplify some stuff. So I could, here cancel mass, since it is in fact in every term. And then I would subtract some terms over, so I'm going to get g delta y minus mu g cosine theta times displacement, and that's equal to 1/2 v squared. So multiply both sides by 2, right? And then I'm going to have to square root, so I'll get 2 g delta y minus mu g cosine theta times displacement. All of this is under a square root, and that would give me my final speed. You're going to get the exact same answer no matter how you do it. But for me, especially if there's no friction, right? This is the much simpler and easier way to go about this in terms of our ramps. Now, ramps are important because they could be one piece to a problem, to an equation. So they could be the first half of, I don't know, bitk. What's bitk? Or you know, some other scenario where we have them launch off a table or something. So hope this helps with ramps. Smash that like and subscribe. Peace out. Until next time, happy review.